thank you very much for asking me to speak at the Rachel Carson Distinguished Lecture Anniversary Series. I'm really honored to have been invited. What I'm going to talk about today is incorporating air and water pollution into the national income and product accounts. So environmental economists, beginning with Nobel laureate William Nordhaus, have urged that satellite accounts for air and water pollution be added to the national income and product accounts. Satellite accounts, an example would be accounts for unpaid household work, focus on a particular part of the economy. They're reported as an adjunct to the national income and product accounts. What Yongjun Park and I have done is to summarize information on air and water pollution that's currently available from the US EPA, information that could be input into satellite accounts for air and water pollution. So I'm going to begin by discussing why I think satellite accounts for air and water emissions are really important. Then I'm going to focus on accounts for local air pollutants like particulate matter, sulfur dioxide, nitrogen oxides. These are pollutants whose effects depend on exactly where geographically they're emitted. Because I believe that it's very important to translate emissions into monetary damages, I'm going to focus on the work that colleagues Nick Muller, Rob Bendelson, and Bill Nordhaus have done to accomplish this. I'm also going to talk about what EPA has done, including recent estimates of damages per ton of pollutant by sector. Then I'm going to talk about satellite accounts for carbon dioxide and other greenhouse gases. The Bureau of Economic Analysis, which does the national income and product accounts, has already begun to construct satellite accounts for greenhouse gases. As we know, their effects on the world's climate is independent of where geographically they're emitted, but valuing them is very difficult. If we emit a ton of CO2 today, 300 years from now, about 30% of that ton is still going to be affecting the climate. So making these valuations so far into the future is really challenging. The question I'm going to raise is whether EPA's estimates of the social cost of carbon, which were recently approved and used at the end of 2023, could be used in satellite accounts. I'm going to end by discussing satellite accounts for water pollution emissions to surface water bodies. Compared to the resources that have gone into valuing damages from local and global air pollution, the valuation of damages from water pollution, I would say, is still in its infancy. But I think here that progress is being made. So, why are pollution satellite accounts so important? For decades, researchers have shown that the externalities associated with air and water pollution are really significant. If you look at work by Muller, Mendelson, and Nordhaus, based on what I would call conservative estimates of damages, they estimated that the damages from local air pollution in 2002 amounted to about 2% of US GDP. It's also true that we spend a lot of money to reduce pollution. Otherwise, we would have more damages than estimated. And I think that it's important to look both at the trends in emissions and also the expenditures that are made to reduce emissions in order for us to understand what progress we're making on the environmental front. I also think that the general public, corporations, members of Congress will pay more attention to these satellite accounts if damages associated with emissions are monetized. Let's face it, people care about the dollar value of damages more than they care about the number of tons. I'm going to focus on the damages associated with air and water pollution with an emphasis on air pollution. Okay, so if we want to look at Damages from air pollution, we have to start by measuring, emissions to air by emitting sector. So what you're going to see on the next slide is the format of the UN core air emissions accounts. These are going to include both local and global pollutants, and they're in the format that they would be presented as part of a satellite account. The local air pollutants are shown above the line. These include carbon monoxide, NOx, SO2, fine particles. EPA provides estimates of these from the National Emissions Inventory every 3 years. Greenhouse gas emissions, CO2, methane, nitrous oxides, are shown below the line, and they're provided by EPA annually by sector. So when you look at this table of a core air emissions account, these are frankly dummy numbers. So you shouldn't focus on the numbers, but you should focus on the titles. These would be reported by industry, by agriculture, mining, manufacturing, by households, in terms of how they are, in what capacity households are emitting them. As I said, you would have both local air pollutants and also greenhouse gases. So how do you go from emissions to monetize damages for local air pollutants? Well, the first thing you have to do is to use air quality modeling to translate emissions into ambient air quality. Suppose that a power plant emits 10,000 tons a year of sulfur dioxide. This is going to be released and change ambient SO2. It's likely to be transformed into secondary particulate matter, and those changes are going to be modeled with an air quality model, something perhaps like CAMX. In order to do this, you're going to need emissions data by detailed geographic location, not just the aggregates you saw on the previous slide. Once you know how the SO2 has been translated into, let's say, PM 2.5, you've got to look at the impacts of that change in PM 2.5 on health, on agricultural output, and on other endpoints that could be affected. Once you have these endpoints, perhaps changes in heart attacks or cases of asthma, you're going to want to monetize these changes, do this for all the endpoints, and then finally, you're going to need for the satellite account to actually trace these back to the 10,000 tons of SO2 that was emitted in the first place. Okay, so one of the first attempts to comprehensively, sorry, I'm going to put things on my screen here. One of the first attempts to comprehensively value local air pollution damages by sector was an article by Nick Muller, Rob Mendelson, and Bill Nordhaus, which was published in the American Economic Review, a top economics journal, in 2011. What they did was to take the 2002 National Emissions Inventory and an integrated assessment model to estimate what they called gross economic damages from air pollution by sector. You will see their results. I think it's fair to say that this provided guidance, especially to economists, to mainstream economists, for future efforts to determine the marginal value of damages by pollutant and sector. Importantly, this article made it clear what the key pollution outcomes are that drive the monetary estimates of air pollution damages, and that's true to this day. And what drives them are the impacts of fine particles and ozone on adult mortality, and also how you value the premature mortality caused by, associated with these pollutants. So to go into a little bit more detail, what MMN, I will refer to them as, did was they took the National Emissions Inventory for 2002, They ran an air quality model to reproduce baseline concentrations of ambient PM2.5 and ozone throughout the country. And then they estimated a series of source receptor matrices to link a marginal increase in emissions of each of 6 pollutants, the ones that are listed here on the slide, on ambient PM and ozone. The impact of the emissions is going to depend on the county where they are emitted and also the stack height. And so they constructed these source receptor matrices for each of the 6 pollutants for over 3,000 counties and for emissions at 3 different stack heights. After they did this, the impact of an emission of, say, a ton of PM2.5 in Los Angeles County was estimated in terms of its impact in other counties on health and other endpoints. Damage functions were used to do this, and then the authors valued marginal damages. And to give you a feel for this, on the next slide, which is a map, what this is showing you is the marginal damages from emitting a ton of PM2.5 at ground level. This is in the year 2002. The damages here are in $2,000 per ton. Suppose I focus on Los Angeles County, which is outlined here in black. What this means is a ton of PM2.5 emitted at ground level in Los Angeles County would cause between $20,000 and $88,000 in damages. A ton emitted in other places, for example, San Bernardino County, is not as damaging. Not as many people are exposed to it. But what is being calculated here is for emitting that ton at each possible place, each possible county in the US, the authors have calculated what the damages are from that ton. Not surprisingly, you can see very large damages in densely populated areas like the New York metropolitan area, Chicago, parts of Florida, and so forth. So having estimated these marginal damages and figuring out exactly what the damages were from all 6 pollutants in 2002 rather, this table is aggregating those damages actually by sector. Okay, so these are again the gross external damages from the 6 pollutants in 2002, measured in $2,000. You can see that the large damages are coming from the highlighted sectors, from agriculture and forestry, where damages were estimated to be $32 billion. Utilities, the highest, $62.6 billion. Transportation, waste management, construction, all big contributors. Manufacturing. And if you sum the damages from all the sectors, it comes out to $184 billion. So we'll focus next on a single sector, coal-fired power plants. The purpose of this is to show you both how important different types of the 6 pollutants are in terms of forming damages, and also how important different categories of damages are. So for coal-fired power plants back in 2002, the largest damages came from sulfur dioxide emissions. Many of those emissions were transformed into fine particles. The PM2.5 here means directly emitted PM2.5, PM10 directly emitted PM10, and so forth. So the mortality impacts of those SO2 emissions were valued here at $44 billion, and they contribute more to premature mortality than any other pollutant. It's also the case, if you look at the different categories of damages, premature mortality is overwhelmingly, and we can also go to the last column here, the largest category. There are clearly some damages associated with morbidity, agriculture, visibility, but they are swamped by mortality damages. So it's important to talk about how is premature mortality valued. This will play a role actually in the rest of the talk. So what they did was to take EPA's value per statistical life, and to define that, the value per statistical life is the amount that people would pay to reduce their risk of death by a small amount, aggregated over risks that sum to one statistical life. So if each of 10,000 people would pay $200 over the coming year to reduce their risk of dying by 1 in 10,000, we would on average talk about saving one statistical life, and the value of that, what people would pay to save that statistical life, is 10,000 times the $200 or 2 million. So EPA estimates compensation for risk of death on the job in order to estimate what people would in fact pay to reduce their risk of death, or what they would have to be paid to increase it if they're working in a risky job. And again, I don't have time to go into this, but the VSL from EPA in $2,000 was 6.3 million. What MMN did was to say, we're going to apportion this VSL to a value per life year saved. We're actually going to take the 6.3 million, divided by the discounted remaining life expectancy of the average worker in an hedonic wage study, and get a value per life year saved and value premature deaths by the number of life years lost times the value per life year saved. When you use their approach, their total damages come out to be the 184 billion that you saw on a previous slide, which was about 2% of GDP in 2002. If you applied the value per statistical life to everybody, regardless of their remaining life expectancy, the damages would be 460 billion, and that would be over 4% of GDP. So it definitely matters how you value mortality. And it also matters what dose response functions, what exposure response functions you use to relate premature mortality to fine particles in ozone. Okay, let's turn to EPA. So EPA developed the apparatus necessary to value local pollution emissions back in the 1990s. It was then that the agency began to conduct cost-benefit analyses of the Clean Air Act. This was required by Congress in Section 812 of the 1990 Clean Air Act amendments, and this meant that EPA had to develop the apparatus to go from emissions or changes in emissions due to the Clean Air Act to changes in ambient air quality, to damages, and then valuing the damages. So recently, EPA has released estimates of damages per ton of pollutant for many different pollutants and many different sectors. As the slide says, in 2022, EPA released estimates of the cost per ton of pollutant for 21 sectors. You'll see the results in a minute. And for 5 pollutants, using the 2017 emissions inventory. My slides are going to be made available, and when you get them, you can click on the link and actually see the website that describes all this. But basically, EPA used air quality modeling. They used CAMX to estimate a source receptor, or source receptor matrices, I should say, for each sector pollutant combination. They did this at a 12-kilometer by 12-kilometer resolution. And then they looked at the impact of the changes in ambient PM 2.5 and ozone on health at the same resolution using software called BenMap, which goes from changes in ambient concentrations to changes in health and other endpoints, and then values those. So an important point here is that the mortality effects of PM and ozone in EPA's calculations constitute 98% of monetized damages. The values you're going to see in a couple of slides are using a 2016 BSL of 10.7 million, but the important thing here is that the bulk of these damages are from mortality due to PM and ozone. Okay, what you're going to see on the next two slides are actually maps that are input to these damage estimates. And the first map is showing you the impact on ambient PM 2.5, annual ambient PM 2.5 of oil and gas extraction. Okay, this is extraction in the year 2017. The darker the colors, the greater the increase in mean annual PM 2.5. In terms of the red, which is increasing it by 0.3, at least 0.3 of a microgram per cubic meter, those effects are rare. They're occurring in Southern California and in North Dakota. In most places, you're getting much smaller impacts on annual average PM 2.5. The orange is between 0.1 and 0.2 micrograms per cubic meter. The yellow actually under 1/10 of a microgram. The results are very different when you look at the impact of wood burning from residential wood stoves. Here you have increases in annual ambient PM 2.5 of greater than 0.3 of a microgram per cubic meter in many parts of the country. Again, these are in populous parts of the country where residential wood burning is being done. And as I say, this sort of analysis underlies the figures you're going to see on the next couple of pages. So what is being shown here for each of these sectors, they actually, as I say, are over 20 of them. You're looking at the impact of either directly emitted fine particles or precursors of secondary particles, SO2, NOx, and ammonia, on PM 2.5 damages. This is being averaged across the whole country. And for example, for the oil and natural gas that we just looked at, a ton of directly emitted PM 2.5 has on average damages of about $100,000. Not surprisingly, for residential wood stoves, those damages are way larger, almost 5 times as big. So I'm not going to have a chance to go through this. You'll see the slides. Precursors of ozone are also evaluated, and this is done for many different sectors. Okay, so the question is, can EPA's approach, which we just saw very briefly, be used to compute satellite accounts for local air pollution? There is the fact that the National Emissions Inventory currently comes out every 3 years. It would be difficult to do the satellite accounts on an annual basis. There are some technical details. For example, the National Income and Product Accounts are interested in what residents of the US emit, regardless of where they live, versus what's emitted in our territories. This is a small matter. I don't think it can be resolved. And of course, EPA's emission categories would need to match sectoral descriptions of the economy that the National Income and Product Accounts use. Valuation raises more problems. The approaches I've described are valuing the marginal impacts of emissions. As I said, I think what should be concentrated on are the mortality impacts of PM 2.5 and ozone. EPA's current value per statistical life is based on hedonic labor market studies. So they're measuring implicitly the price for bearing additional risk in the labor market. We could view that as a market price, but there are various details here that need to be worked out, and I don't have time to go into them. Okay, so let's move on to greenhouse gases. So EPA reports emissions of greenhouse gases by sector annually. The Bureau of Economic Analysis has constructed pilot supply and use tables for 2017. You're going to see one on the next page. The big question is, can these be valued using EPA's social cost of carbon? The social cost of carbon measures the present value of net damages from emitting an additional ton of CO2 in a particular year. It includes changes in net agricultural productivity, changes in energy use, human health, property damage from increased flood risk. I will tell you how the social cost of carbon, at least from the 50,000-foot view, is computed. But first, let's look at this supply and use table for greenhouse gases. These are ones emitted in 2017. And what's been done here is to report not just CO2, but methane, nitrous oxide, weighted by their global warming potential. So the total here in terms of CO2 equivalent is 6.4 billion tons. And if we look at the big emitting sectors, we have manufacturing, utilities. We should start with utilities, manufacturing, households. You add these together and they're about 2/3 of the 6.4 billion. The other question is, how high is the social cost of carbon? If we were to use EPA's most recent estimates, the social cost would be about $200 per ton of CO2. If you multiply that by 6 billion, you get $1.2 trillion. And we are talking about large damages. So the question is, how do you calculate the social cost of carbon? Okay, so this is a short course in how to calculate the social cost of carbon. As I say, the problem, or said a minute ago, the problem is that the ton emitted today will remain in the atmosphere, or at least part of it will remain for a long time. So calculations are usually done over a period of 300 years. We need to know what the world is going to look like over the next 300 years. Obviously, a very tall order. This requires projecting per capita income by country, ideally, population also by country, emissions of greenhouse gases over this time period, because the damage of today's ton depends on how much is going to be emitted in the future. So that's difficult. It has been done, can be done using expert elicitation, and for things like GDP per capita and even population econometric methods. Then you have to go and you have to say, okay, look at the future path of CO2 emissions with and without this pulse, and use climate science to tell us how that's going to change mean global temperature. What will that look like in a baseline, and then after this pulse has been added? Then, of course, you've got to downscale that to regional temperature changes, sea level rise, ocean acidification, and then, not finally, but penultimately, step 3 is attempting to monetize the damages that these changes in temperature, sea level rise, and so forth will cause. But given they're going to last for a long time, they have to be discounted to the present. And as it says here, the social cost of carbon is the per ton difference in the present value of damages due to this pulse of CO2 emitted today. Okay, so the US government began calculating the social cost of carbon in 2009 during the Obama administration. The interagency working group is the group that actually does the calculations. They continued with their calculations through 2016. They were disbanded by President Trump in 2017, but they were reconstituted by President Biden, actually the first day that he came into office. So what the group did was to look to 3 integrated assessment models that essentially do all of the steps that were described on the previous slide. There's Bill Nordhaus's DICE model, the Anthoff-Toll Fund model, and the Page model of Chris Hope. I won't go into the details of how they modified to some degree these models. You can, again, read about this. But basically, they ran 150,000 Monte Carlo runs of these models for each of 3 discount rates. The discount rate matters a lot. And what you're going to see on the next slide is the distribution of the social cost of carbon. Remember, there's great uncertainty in every stage of computing the social cost of carbon. So what we're looking at here are distributions of damages with a relatively high discount rate of 5%. The distribution is more concentrated towards the vertical axis rather, and the mean social cost of carbon, this would be for a ton emitted in 2020, measured in 2020 dollars, it would be $14. The value that was emphasized was the 3% value, and that is a 3% discount rate, which would lead to a social cost of carbon of about $50 a ton. The social cost of carbon would be higher if you used a lower discount rate. So when President Biden, as I say, became president, these values were adopted. They're referred to here as interim estimates. I hope you can see the title of the slide. And that's fine. What happened was that the federal government went to the National Academy of Sciences, to the National Research Council, to ask for advice on how to improve the social cost of carbon. And so what we advised, I co-chaired this committee along with Richard Newell, who's currently the president of Resources for the Future. We recommended that EPA should just construct its own integrated assessment model. It should construct a socioeconomic module, a climate module, a damages module, and then discount the results. Each module would be developed based on expertise within the relevant discipline, and uncertainty would be quantified at each stage and transmitted to the next stage. I'm not going to go through exactly how these recommendations, and there are further recommendations which you can read if you look at the slides, but I don't think we have time to go through them. What was done was for EPA, with the help of researchers, really, I would say, not just in the United States, but elsewhere, released estimates, new estimates of the social cost of carbon in the fall of 2022 that satisfied all of the NRC recommendations. RFF's probability distributions over socioeconomic pathways, which were published in Nature, were used. A Earth system model called the FAIR model was used, and there were 3 new sets of damages going beyond DICE, Fund, and Page, generated by RFF that examined impacts of temperature changes on mortality, agriculture, energy, and sea level rise on coastal damages. The Climate Impact Lab at the University of Chicago developed another model at fine spatial scale, looking at impacts on mortality, agriculture, energy consumption, coastal damages, and labor supply. And added to this was a meta-analysis by Howard and Sterner of the literature on damages associated with climate change. So these led to the estimates that you're seeing on this slide. So this is, again, the damages in 2020 dollars of emitting a ton of CO2 in the year 2020. These are estimates which were adopted after peer review. There was extensive peer review and public comment, and these were adopted by EPA in 2023. And as you can see, the ton emitted in 2020 is now valued at about 5 times what you saw, sorry, 4 times, so early in the morning for me, the $50 amount. So as I said, if you were to adopt this value, you would indeed have 6 billion tons at $200 being $1.2 trillion. It would be large damages. Now, what are the issues from a national accounting perspective? These are global damages. They are actually damages to all countries in the world. When we emit a ton of CO2, it affects the Earth's climate and affects everybody on the planet. These bullets are my bullets. They are not the Bureau of Economic Analysis bullets. We do include exports in the national income and product accounts. We are measuring here damages from exports of pollution of CO2 and other greenhouse gases. I don't know, whether this would be the official view, but it's important to realize that these are global damages that I've shown you. The valuation of these damages, mortality damages are a big component of the $200, and they are valued using EPA's value per statistical life based on hedonic wage studies. This is transferred to other countries using an income elasticity of 1, energy consumption, agricultural impacts, and sea level rise, certainly in the DSIM model, are valued using market prices. Okay, I will move on to accounts for water pollution emissions. So you would need to begin with a physical supply table for gross releases of substances to water. This is a mock-up from a UN document. The numbers are just dummy numbers, so what you want to focus on is the format of the table. And so what you have here are emissions that are received by the environment in surface water, biochemical oxygen demand, suspended solids, heavy metals, phosphorus, nitrogen, and so forth. The industry or sector that is emitting them would be distinguished. And finally, you would get an estimate of total emissions. The question is, do the data exist to populate tables like this? So in terms of point source emission data, the National Pollutant Discharge Elimination System, NPDES, covers emissions from point sources, including animal feeding operations, fish farms, industrial operations, as the slide said, mining, oil and gas drilling, stormwater discharges, and so forth. So these data are reported in discharge monitoring reports. That's great. We all know that non-point sources, for example, agricultural runoff, are a really important source of water pollution. So how would these be measured? So there is a model which goes by the acronym of HAWKS, which is used by EPA to model ambient water pollution. So the HAWKS model models river and stream water quality at the watershed level. It simulates the effects of crops, soils, land uses on sediment, on pathogens, nutrients, BOD, dissolved oxygen, and so forth. If you wanted to look at the impact of water pollution broadly defined on a particular watershed, you could use HAWKS to estimate the non-point source impacts and then add point source loads from NPDES. This would give you estimates of dissolved oxygen, total suspended solids, BOD, nitrogen and phosphorus, fecal coliform levels on the watershed from emissions over a particular period. The difficult part will be actually valuing changes in these pollutants. There are multiple impacts of each of these pollutants on water quality, on aquatic life, on commercial fisheries, and so forth. But valuation is much more difficult, and it's more difficult to do for the entire country. So, when you have a dose response function relating or exposure response function relating PM 2.5 to premature mortality, that's a function which can be used throughout the country. When you want to look at the impact of water pollution on housing values, on recreational benefits, on recreational fishermen, on boaters, and so forth, these are values that are going to vary throughout the country. It's going to be very difficult, much more difficult to estimate these than it is to estimate the health impacts of a change in PM 2.5 at the 1 kilometer by 1 kilometer level. Non-use values are important. These are what people would pay for improvements in water quality, even if they never fish or recreate at national parks. I would count myself there. I would be happy to pay to make sure that rivers and streams in this country are not polluted. I care about that, and I care about the fact that other people want to use them, but this is a non-use value. These are hard to estimate other than by asking people directly for them. The, how shall I say it, the parallel platform to what I referred to as BenMap is BenSplash. It quantifies and monetizes water quality improvements. If EPA is going to issue a regulation regarding, let's say, emissions from feedlots, it will use it to estimate the benefits of that regulation. BenSplash looks at 6 pollutants: dissolved oxygen, fecal coliform, nitrogen, phosphorus, BOD, and total suspended solids. It combines them into a water quality index, and then it takes a literature which directly is asking people to value some of these endpoints that you're looking at here, and then a meta-regression of the studies is used to value the water quality index. This is something which is in development. Many studies are currently coming out on, for example, the impacts on housing values of changes in ambient water quality, but this is not as developed as it is for ambient air pollution. So, and this is my last slide. I hope I'm on time, Jack. What I would conclude by saying is this: there is certainly sufficient data for an air emissions satellite accounts. These would be accounts in terms of tons emitted. As we saw, definitely for greenhouse gases, these already have been done. For local air pollutants, in terms of tons, these also could be constructed from the National Emissions Inventory. They would have to be adjusted to meet sectors used by the Bureau of Economic Analysis. I think it's possible, and certainly environmental economists have been monetizing air pollution damages, both local air pollution damages. You saw some of EPA's current estimates, and also using the social cost of carbon. By the way, there is also a social cost of methane and a social cost of nitrous oxide. I think that accounts for water emissions are possible, but monetization of damages, I think, really remains to be something in the future. So I hope I've given you some understanding here of what's possible and what I hope will eventually take place in terms of satellite accounts for air and water emissions. I think it's very important for the country to focus on these, and I think constructing satellite accounts will be a way of doing this. So I will end here.
Yeah, thank you so much, Professor Klaper, and for your fantastic presentation. And this is very insightful and very informative. Now it's time for questions. Again, the audience is welcome to post questions in the Q&A box. And actually, I already see a question there now. Question from Tom Dees. He said, yeah.
Hi, Tom. Slow. Yeah.
So a bigger picture question on the role of national accounts in decision making. In 1934, Simon Kuznets, in a foundational document on national accounts, advised that the welfare of a nation can therefore scarcely be inferred from a measurement of national income as defined above. So how good is this advice today? How are the adjustments to the national accounts you have so clearly articulated used in decision making? How should they be used?
Very good question, Tom. I mean, in terms of, I would say, satellite accounts that have been around for a long time, certainly household production and estimating the value of household services that are unpaid has been used for a long time. I mean, in terms of how does it affect decision making, that's a harder question to answer. But I think, most economists would say, oh my gosh, those services are worth about 20%, 25%, maybe 30% of current GDP. In terms of, how would the satellite accounts be used for environment? I mean, my view is that it would make people sit up and take notice in a way that they otherwise would not if you didn't give all of this data, how shall I put it, the imprimatur of the national income and product accounts. In terms of how would it be used, I think it would be used indirectly. As I say, I think in many ways, the main consumers of this would be the general public, members of Congress, NGOs, corporations. I mean, EPA certainly has all of this information that I described today at its disposal, and it's using it in evaluating the benefits and costs of regulation, in actually motivating what regulations are being suggested and implemented. So, the agency already is using this, but I think the important impact that it would have on policy would really be indirect. It would be that now the general public will be more aware of this, and certainly other decision makers, as I say, members of Congress, other, various stakeholders, corporations would become very much aware of it. So I think that would be actually probably the main benefit of constructing these accounts.
Yeah, thank you so much. That's great. So you mentioned some damage will last for a long time, and but some damage will not show up until many years, or sometimes maybe even decades later. How do you estimate those damage that you cannot see, until many years later?
Okay, well, first of all, the beginning, how shall I say it, part of estimating the social cost of carbon, going from estimates of emissions to impacts on climate, that has been, I would say, much better developed than the other stages, thanks to climate scientists and groups of scientists who have run groups of models to estimate these impacts. So, I mean, when we were on the National Academy NRC committee, we had climate scientists, Chris Forrest, Bob Kopp, Miles Allen, Inez Fong, who actually did help to try and construct something simplified, which was this FAIR model, finite amplitude impulse response, and make it something that could be used more readily in the calculations. Admittedly, this issue of of projecting what the world will look like, if I had more time, I would show you the probability distributions that were estimated for population, for per capita GDP by region of the world, for CO2 emissions. I mean, all of this is done taking into account the inherent uncertainty, and that is really being transmitted into the analysis. So admittedly, I mean, the hard part of this is definitely the time dimension, and that does make things difficult. All one can do, I mean, we can't avoid the time dimension. We can actually quantify the uncertainty that's involved. We can do sensitivity analyses. And if you were to look at EPA's most recent document that incorporates all of this, you would see that all being documented. So I think I will just stop there.
Excellent. Thank you so much. So the next question is from Saha MD Article Hack. Sorry, I could not pronounce all the name right.
Okay.
Yeah. Thank you for your great presentation. I was wondering how cultural factors would be considered in modeling the impact of pollution and also in terms of mortality. And our war modeling-based data can tell us what to do for specific region that face different types of climate events and social-economic challenges. So basically, how you address those kind of situation for different cultural and different regions. Yeah.
No, very good. Well, first of all, in terms of the modeling, if you look at what has been done at the University of Chicago to model temperature-associated mortality, which does take into account adaptation that will occur as countries become wealthier and they're able to adapt to hotter environments and so forth. I can't describe all of what's done there, but there is a lot of detail that's been taken into account. As it turns out, tomorrow I'm going to be talking at the World Bank about adapting to climate change in South Asia. And so in terms of being aware, and I'm going to focus on cities in India, in terms of being aware of these threats and doing something to try to avoid them, there is an Ahmedabad plan to deal with heat waves, essentially, which involves everything from trying to actually give people some warning of when a heat wave is likely to happen, to try and provide actually potable drinking water and shelters when that happens, to actually just make people aware of the fact that they will need to adjust as best they can when these heat waves occur. The Ahmedabad plan has actually been adopted, I should say, by 17 other cities in India. So, I mean, there is awareness of these issues. I mean, there are other types of adaptation in terms of, green roofs or trying to plant more greenery to reduce the urban heat island effect. So I think that adaptation is something that is of concern. In fact, if you go, there is a UN website that actually will present some of these estimates from the Climate Impact Lab for different cities. I've looked only at India, but under different climate scenarios, what's likely to happen. So I think that, adaptation to this is very important, and that people, are aware of this, and to the extent that it's possible to do this, are taking measures to adapt.
Yeah, thank you so much. Also, another question would be, you mentioned estimated the social cost of carbon, and in part based on projection of population. But also you mentioned the pollution from household sectors, and it seems like the worldwide, the number of households increase much faster than population size. So if you are going to based on the household numbers to estimate the social cost, what kind of difference would be between using population size versus a household number to do the estimation?
Well, first of all, to estimate, and I emphasize distributions of possible emissions. I mean, what you're looking at here is estimates of how energy use is going to evolve over time. You're also looking, quite frankly, at policies that will evolve. I mean, to what extent will people, and how fast, hopefully, will people switch to renewable energy sources? All of these things have to go into these estimates. As I say, if you were to if you go to the Resources for the Future website, where a lot of the description of how this was done and pictures of these distributions are given, I think it would be easier to appreciate all of what underlies these estimates. And these are highly uncertain, but the important thing is to quantify the uncertainty.
Yeah, thank you so much. I wish we had more time, but it's already past the time.
Yeah, it is.
Yeah, so thank you
Yes.
so much again for your terrific presentation. Also, thanks the audience for the participation. So have a nice day, everybody, or have a nice evening, depending where you are.
Right.
So appreciate
Thank
it.
you for listening. Yes.
Yeah, that's
very
great.
much.
Yeah.
Okay.
Yeah.
Goodbye. Yes.
Yeah. Goodbye.